like to do now, though, is to move on to the reality, because it's nice that we have a standard normal distribution with a mean of 0 and a standard deviation of 1, but most variables are not distributed with a mean of 0 and a standard deviation of 1. In fact, our tabletops, maybe they have a mean of 100 centimeters, for example. But the following theorem provides the relationship between any normal distribution, any variable that's normally distributed, and the standard normal distribution. And since we know, it's our standard normal distribution, since we know a lot about the standard normal distribution, it helps us with the calculations, we can use this theorem then to help us find interesting information about our real product, about our real random variable. So, if x is normally distributed with a mean of mu and a variance of sigma squared, then the variable, the new variable, x minus mu divided by sigma, follows the standard normal distribution. So let's have a look at this in a little more detail. If we want to convert between normal distributions, let's start with our tabletops. We have a mean of 100 centimeters and a standard deviation of 25 centimeters. Is not very good tabletops, but that's our normal distribution, which we have sketched here. And we're interested for looking at our very long tabletops. We want to know how many information about tabletops that are 125 centimeters in width. So the first thing we do, we are going to subtract from every value, here's our tabletop width here, from every one of these values, we're going to subtract the mean. So the mean, which was 100, right? Subtract 100, and we move it over to 0. From the extreme here, 200, we subtract the mean, we get 100. So we've essentially shifted our distribution of our real value so that it's centered over 0. That's the first step. The second step is we're going to rescale the x and y axes by dividing every one of those variables by the standard deviation. So the standard deviation there is 25, so here our extreme value of 100 becomes 100 divided by 25 is 4. The 0 stays the same. And what we have here then, once we've made these two, transformations, is we have our variable z. We have our standard normal variable z, which is centered at 0, mean of 0, with a standard deviation, again not terribly well shown here, of 1. Mean equals 0. And when we look, remember we were interested in this x is 1.25. Look at that x value. Put it in to our, and look exactly at particularly that one. We get 125 minus 100 over 25 equals 1. And what that means, if we looked it up on our table, that value of x is 1 standard deviation greater than the mean. And now we can use our tables. We can calculate what percentage of our population would be below x equals 125. We can calculate what percentage would be above using our standard normal tables. Let's do an example. So, random variable, normally distributed with mean equals 2, and variance equals 0.0025. This, of course, then will give us a standard deviation of equal to 0.05. Take the square root. Now, we're interested in the proportion of our population that is below 1.87. So what we're going to do is our conversion. Now, it looks like a lot, but it's not. We're going to subtract from every value of x the mean, 2.0, and divide by the standard deviation. So we do this for our x, and we do it for our 1.87. And now when we do this, we get our familiar standard normal variable z. And here we get a number. Here we calculate a number. We get minus 2.6, and this we know how to do. We look it up on our table. We say the proportion of our population with z less than minus 2.6, where z is distributed according to the standard normal, is in our table only 0.47%. Very small. Now, remembering back to our table, this is minus 2.6 standard deviations below the mean. You're not going to have a lot of of your random variables below that. So this makes sense, a low value. What about the probability that x is greater than a certain value? Greater than 2.2. Do the same thing. Our random variable will be z. We don't have to write it. We're going to take our 2.2, subtract the mean, divide by the standard deviation, and we get the proportion of the population that is greater than 4. Now, I didn't even bother with a table here. 4, in normal distribution terms, if you have greater than 4 standard deviations above or below the mean, there's not going to be a whole lot above that. It's going to be very, very small, nearly 0. It's very unlikely that we will have values that are greater than 4. So of course, if you use a computer, you get a small value for that. But for our purposes of this course, we're going to say, for our practical production, we're going to get very, very unlikely that we will get, for a random variable x that is normally distributed with a mean of mu and a very tight variation, nothing above 2.2. That makes sense? Okay, a couple more exercises. Find the proportion of the population x, same population, mean of mu, I'll write that up here. Mean is 2.0, sigma is 0.05. What proportion of our population is between 1.9 and 2.1? So we look now at our z value. We transform the 1.9, and the 2.1. We do what we did before. We look at our table and we subtract the CDF functions, and we get that 95.4% of our population will be between these two values. And that kind of makes sense, right? The mean is 2. 2 is right between these two values. You would expect that a high number. And in fact, we learned that 95% was roughly about 2 standard deviations. So does make about sense. We can also do it the other way around, though. We can say, well, listen, we would like to know the value of our population where 5% of our random variables are less than some unknown value. Before, we were given the value and we're looking for the percentage below that or above that. Now we're saying, we would like to know if we have a population, 2.0, standard deviation, 0.05. What will be the t value where we have only in this case 5% of the population will be below that? So looking at the picture, we can already know that it'll be less than 2. Do our transformation though. So we've got z, we transform our t, we look up in our table 0.005, and we find the z value. We find the z value. we can say, if we look up this in the table, it'll be at a z value of minus 1.645. Try that on your own. And we can solve for t. We'll find that t equals 1.918. 1.918. It's our variable t. And that means 5% of the population is below 1.918 for a random variable that is normally distributed like that. Okay? Now, let's move a bit into the more practical quality side of things. Another example, if d is the diameter of bolts, a bolt is a bit like a nail, you hold things together with a bolt, and this is in inches, and we know that the diameter of these bolts, the diameter here, is distributed at a quarter of an inch with a variance of 0.01 squared or a standard deviation of 0.01. Now, this is where we become more into the practical things. The specifications for the bolts are 0.24 plus or minus 0.02 inches. This could be the real situation. We are running our line. We are making these bolts. And we know, because we can measure them, that our diameters are at 0.25. We know the specifications. We want to know in our production line how many bolts are we going to have to throw away? What proportion of the bolts are outside the specifications? So we need to know the proportion of the diameters that are less than 0.22 plus the proportion that are greater than 0.26, and that comes from here. The lower spec limit is going to be 0.24 minus 0.02, 0.22 inches. And the upper spec limit is going to be 0.24 plus 0.02 inches, which is 0.26 inches. So we're interested in looking, draw this again. Oops. The lower spec limit, upper spec limit, we have our mean. Terrible picture here. We're interested in these two parts of our distribution. So now here we have to do to use our table, we have to do our transformation. Instead of d, we're going to look for z, and we're going to transform the 0.22 and the 0.26 by subtracting the mean and dividing by the standard deviation. Now if we do that, because this is a convenient problem, we find the proportion of the population less than -3 and the proportion greater than 1. Go to our tables, look at our tables, and we get following values from our tables, and this shows us that 16% of our bolts are outside specifications. Let me write that down. 16% of the bolts are outside specification. I'm going to throw them out. This is not good. That is not a good production line. So, how can we improve our process? So do you remember the sharpshooter? There were the sharpshooters that were missing the target, and there were 2 of them. So there was one that was always off the target, and the other one was kind of around the target. So what we did was we moved the one that was always off target onto target, and that's called centering. So if before we had a process mean of equal to 0.25. Now the specification, the spec, was 0.24 plus or minus 0.02. These did not coincide. So if we change our process, we see one thing we can change, and we make our process so that the mean, instead of being at 0.25, is at 0.24. And then we look for the parts that are out of our specification limits. So this time, exactly the same thing. Here's the 0.22, here's the 0.26. But this time, instead of 0.25, we've got a new process centered. Haven't changed the standard deviation. We've centered our process. And of course, this is then symmetric on either side. And if we look up on our tables, we find instead of 16%, just by centering our process, not changing the standard deviation at all, we reduce the proportion out of spec. Try to draw this. Difficult. So before, we had a mean of 0.25. We had a normal distribution. And we had a lower spec limit of 0.22 and an upper spec limit of 0.26. And when we added this together and this together, this plus this gave us 16% out of spec. Now I don't have another color pen. This is our target, 0.24. If we shift our distribution so that it's over the target, these two little tails will be much smaller. Difficult to see here on my picture, but these two small tails will only be 4.56%. So, centering a process will improve the process conditions. Further improvement has to come, though, from actually shrinking, reducing the variability of our normal distribution. So here's another example to illustrate that. If we have a random variable x that denotes the life of battery in years, and we know that our battery life is normally distributed with a mean of 5 years and this sigma, variance sigma squared of 0.25 years squared, or a standard deviation of 0.5 years. If any battery failing before 4 years is replaced under warranty, so if you're the battery manufacturer, you certainly are interested, you want to be replacing batteries, what proportion of the batteries need replacements? So how do we look at this one? So the first thing we want to do is we want to write P is less than equal to 4. What proportion of our batteries will fail before 4 years? We change the X, becomes a Z if we do our transformation with our mean and our standard deviation, 0.5 years. And we get the proportion that Z is less than -2, and we can look that up on our table, and we see that 2.28% will have to be replaced during the warranty, because we have most of them fail at 5 years, but our warranty is until 4 years, and there will be a small percentage that have to be replaced. So how can we change this? Well, we can look at improving our process. We can look at reducing the standard deviation. And let's see, we know we can't do much better, but because of cost reasons, we don't want to replace more than 0.5% of our batteries. Otherwise, it's just too expensive for us. So we let sigma apostrophe be the new standard deviation. And our new problem, find the probability that X is, or find the standard deviation such that our batteries will fail, the batteries that fail before 4 years, before the warranty, will be equal to 0.005 maximum. So the same problem, X becomes Z. The 4 we transform, but this is here our new unknown. We don't know this. But we now have defined what our proportion should be. So we look up what Z value is going to be at 0.005, and we find the Z for that value will be equal to minus 2.575. So we have our standard normal minus 2.575. The values in this little tiny, tiny area will be equal to 0.5%. That's what we've looked up. We can solve then for our new standard deviation. Now, before the standard deviation was 0.5, reducing it to 0.3883 or 39 is a 23% reduction in variability. You have to see if your production line can do that and if it's cost effective.